So it's time to talk about the third and final type of ionizing radiation, the gamma ray. Now you know about gamma rays already from the electromagnetic spectrum, but you need to understand where they're coming from in terms of nuclear radiation as well. If an alpha or beta decay happens, sometimes the nucleus that's left behind can have excess energy. The nucleus gets rid of that excess energy by releasing an electromagnetic wave or emitting an electromagnetic wave. And those energies are typically in the range of the gamma rays. They're the most energetic, the shortest wavelength, highest frequency electromagnetic waves. The nucleus does not change whatsoever during this process. The only thing that happens is any excess energy that nucleus has is emitted as a wave. So the element itself doesn't change. It doesn't change isotope. It doesn't change into a different element whatsoever. It stays as it is, but the element, the nucleus, transfers its excess energy as a gamma ray. Properties of these things. Now that gamma symbol is a Greek letter, and you will see it. Sometimes there'll be a little bit more of a loop at the bottom of it. It's just the font that is used on this presentation isn't the clearest necessarily in that one, but that's what it looks like in terms of symbol. Mass, it's an electromagnetic wave. It has no mass. Penetration is the most penetrating because it's got no charge, so it's not likely to interact with electric charges. It's also got a very, very small wavelength, and electromagnetic waves tend to interact only with things that are of a similar size to their wavelength. It's smaller than the atom, the wavelengths of these things, so it's not likely to interact with them. It can do, and it's rarely and occasionally will do, but it is highly unlikely that it will. So it's the most penetrating, can travel long distances, effectively infinite range in air, and it's only really absorbed by thick lead or a few meters of concrete. Ionization wise, because it doesn't interact, because it doesn't have a charge, it is the least ionizing of the types of radiation. They're more likely to travel through things than be absorbed by them. Speed, it's an electromagnetic wave. It travels at the speed of light. It's the fastest. It's the fastest of all the types of ionizing radiations, and it's the fastest that pretty much anything can go at. Magnetic fields, it's got no charge. Doesn't get affected by magnetic fields. It will literally travel in a straight line through a magnetic field. It won't affect it whatsoever. You need to know about two applications of gamma rays. In fact, you need to know about more than that in terms of the kind of things that occur within the electromagnetic spectrum, but linked to particularly this topic, you need to be aware of medical tracers and radiotherapy. Medical tracers use the fact that some isotopes of that are gamma emitters can be injected into the bloodstream and will move around within the bloodstream. They can then be detected outside the body and be used to analyze if blood is flowing to where it should be, or if a certain organ is functioning as it should. So in the example we've got in the diagram below, iodine 123 is absorbed by the thyroid. As it's absorbed by the thyroid will give out more gamma rays than other areas, and because of that the detector can show that if the thyroid is functioning as it should be, there would be more gamma radiation being given out by the patient's neck around the thyroid gland than there would be anywhere else on the body. The other application is radiotherapy. Now, when a tumor develops somewhere that cannot be operated on, say like within the brain itself or the spinal column, then it can be too dangerous to operate with that patient and remove it surgically. Options that exist are then chemotherapy, which is treating it with drugs, or radiotherapy, which is treating it with radiation or gamma rays. What happens is the location where the tumor is found inside the body is determined using medical imaging techniques such as MRI scanners or CT scans. You don't need to know how they work for the GCSE, but they basically are able to pinpoint and create an accurate 3D model of where the tumor is. Gamma rays are then fired at the tumor from multiple angles. This is done to maximize the dose that the tumor receives, but to minimize the doses received by the healthy tissues. So lots and lots of different angles are used. The patient is typically immobilized to make sure that they don't move around and the radiation doesn't go anywhere it's not supposed to. But as you can see from the diagram, gamma radiation still goes through healthy tissue. So there's a risk to that healthy tissue. So a heavy part of the process when looking at radiotherapy is ensuring that the patient will benefit more from being exposed to the gamma rays than they would from any other alternative methods. So risk assessments are always done on the damage that would be potentially caused by the dose of radiation necessary to kill the tumor versus attempting other methods such as chemotherapy or things like that. Key points about gamma rays that you need to be aware of. It's an electromagnetic wave given off by the nucleus of an atom that has got an excess of energy, typically after alpha or beta decay. Emission of a gamma ray does not change the structure of the nucleus at all. It does not change the number of neutrons, does not change the number of protons. They've got no mass. They're the fastest of the ionizing radiations because they travel at the speed of light. They're the most penetrating because of their incredibly small wavelength and no charge. They're the least ionizing for the same reasons. And they're not affected by magnetic fields, particularly because they have no electric charge. They can be used in both medical tracers and in radiotherapy.